The universe is teeming with stars. They come in a dazzling array of sizes, colors, and temperatures. Our Sun is just one star among billions in the Milky Way galaxy, and the Milky Way is just one galaxy among billions in the observable universe. Stars are not randomly scattered throughout space. They are grouped together in vast collections called galaxies. Galaxies themselves are also grouped together in clusters and superclusters. The study of stars is called stellar astronomy. It is a fascinating and complex field that seeks to understand the birth, life, and death of stars. By studying stars, we can learn a great deal about the universe we live in. For example, stars are the factories that produce the heavy elements that make up our planet and our bodies. Main sequence stars are the most common type of star in the universe. Our Sun is a main sequence star. These stars are in the prime of their lives. They are fusing hydrogen into helium in their cores, releasing enormous amounts of energy. The color of a main sequence star depends on its temperature. The hottest stars are blue, while the coolest stars are red. Our Sun is a yellow main sequence star. Main sequence stars come in a variety of sizes and masses. The most massive stars are also the hottest and brightest. They live short, brilliant lives. The least massive stars are the coolest and dimmest. They live long, quiet lives. O-type stars are the hottest and most massive main sequence stars. They are extremely rare. They have surface temperatures of over 30,000 Kelvin and shine with a bright blue light. An example of an O-type star is Zeta Puppis. B-type stars are also very hot and massive. They have surface temperatures between 10,000 and 30,000 Kelvin. They appear blue-white. Rigel in the constellation Orion is a well-known B-type star. A-type stars are somewhat cooler than B-type stars. They have surface temperatures between 7,500 and 10,000 Kelvin. They appear white. Sirius, the brightest star in the night sky, is an A-type star. F-type stars are even cooler than A-type stars. They have surface temperatures between 6,000 and 7,500 Kelvin. They appear yellowish white. Procyon in the constellation Canis Minor is an F-type star. G-type stars are similar in temperature to our Sun. They have surface temperatures between 5,200 and 6,000 Kelvin. They appear yellow. Alpha Centauri A, the closest star to our Sun, is a G-type star. K-type stars are cooler than our Sun. They have surface temperatures between 3,700 and 5,200 Kelvin. They appear orange. Epsilon Eridani, a nearby star with a planetary system, is a K-type star. M-type stars are the coolest and least massive main sequence stars. They are also the most common type of star in the Milky Way galaxy. They have surface temperatures less than 3,700 Kelvin and appear red. Proxima Centauri, the closest star to our solar system, is an M-type star. Giants and supergiants are stars that have evolved off the main sequence. They have exhausted the hydrogen fuel in their cores and have begun to fuse heavier elements. This causes them to expand to enormous sizes. Giants are larger and brighter than main sequence stars of the same temperature. Supergiants are even larger and brighter than giants. They are among the largest and most luminous stars in the universe. Red giants are stars that have exhausted the hydrogen in their cores and have begun to fuse helium. This causes them to expand significantly. They become cooler and redder than they were as main sequence stars. Aldebaran in Taurus is a well-known red giant. Blue giants are massive stars that have evolved off the main sequence. They are still fusing hydrogen in their cores, but they are doing so at a much faster rate than main sequence stars. This causes them to be much hotter and brighter. Bellatrix in Orion is a blue giant. Supergiants are the largest and most luminous stars in the universe. They can be red or blue depending on their temperature. Betelgeuse in the constellation Orion is a red supergiant nearing the end of its life. Rigel, also in Orion, is a blue supergiant. The term dwarf in stellar classification can be a bit confusing. While it always refers to stars smaller than our Sun, it encompasses stars at different stages of their lives. White dwarfs are remnants of dead stars, while brown dwarfs are failed stars that never ignited fusion in their cores. White dwarfs are the extremely dense remnants of dead stars. They are about the size of Earth, but contain as much mass as the Sun. They are incredibly hot when they form, but they gradually cool down over billions of years. Sirius B, the companion star to Sirius, is a white dwarf. Brown dwarfs are objects that are too massive to be planets, but not massive enough to be stars. They are sometimes called failed stars. They can fuse deuterium, a heavy isotope of hydrogen, but they cannot sustain nuclear fusion like main sequence stars. Gliese 229b is an example of a brown dwarf. Red dwarfs are the smallest and coolest main sequence stars. They are much less massive than our Sun and have much longer lifespans. Proxima Centauri, the closest star to our Sun, is a red dwarf. Section 5. Exotic stars. Stellar mysteries. Exotic stars are objects with extreme properties that challenge our understanding of physics. They are often associated with the death throes of massive stars and the bizarre environments they leave behind. Neutron stars are incredibly dense objects that form when massive stars collapse at the end of their lives. They are composed almost entirely of neutrons. They're about 20 kilometers in diameter but can have twice the mass of the Sun. The rapid rotation and strong magnetic fields of some neutron stars make them pulsars, emitting beams of radiation like cosmic lighthouses. The Crab pulsar, located in the Crab Nebula, is a famous example. Black holes are regions of space-time where gravity is so strong that nothing, not even light, can escape. They form when massive stars collapse at the end of their lives. Black holes are invisible, but their presence can be inferred by their effects on nearby matter. Sagittarius A*, at the center of our Milky Way galaxy, is believed to be a supermassive black hole. Section 6. Variable stars' stellar pulses. Variable stars are stars whose brightness changes over time. This variation can occur for a variety of reasons, including pulsations, eruptions, or eclipses. Studying variable stars helps astronomers understand stellar evolution and measure distances in the cosmos. Cepheid variables are pulsating stars that brighten and dim in a regular cycle. The period of their pulsations is directly related to their luminosity, making them valuable standard candles for measuring distances in space. Delta Cephei in the constellation Cepheus is the prototype of this class. R Lyrae variables are another type of pulsating star. They are older and less massive than Cepheid variables, and their periods are shorter. They are commonly found in globular clusters, ancient groups of stars that orbit galaxies. RR Lyrae in the constellation Lyra gives its name to this category. Mira variables are pulsating red giants with long periods and large variations in brightness. They are named after the star Mira in the constellation Cetus, which was one of the first variable stars to be discovered. Section 7. PreMain sequence stars, stellar nurseries. PreMain sequence stars are stars in the early stages of formation. They are still in the process of gathering material from their surrounding molecular clouds. These stellar nurseries offer a glimpse into the chaotic and dynamic processes of starbirth. T Tauri stars are young, variable stars that are still contracting and have not yet reached the main sequence. They are often surrounded by disks of gas and dust, the raw materials for planet formation. T Tauri in the constellation Taurus is the prototype of this class. Herbig AB stars are more massive PreMain sequence stars. They are also surrounded by disks of gas and dust, which can give rise to planetary systems. AB Aurigae in the constellation Auriga is an example of a Herbig AB star with a protoplanetary disk. Section 8. PostMain sequence stars, stellar transformations. PostMain sequence stars are stars that have exhausted the hydrogen fuel in their cores and are in the later stages of their evolution. They undergo dramatic transformations, expanding and contracting, changing their surface temperatures, and shedding their outer layers into space. Red supergiants are massive stars that have evolved off the main sequence and have expanded to enormous sizes. They are cool, but incredibly luminous. Betelgeuse, in the constellation Orion, is a well-known red supergiant. Blue supergiants are massive stars that have evolved off the main sequence but are still extremely hot. They are less common than red supergiants but are even more luminous. Rigel in the constellation Orion is a blue supergiant. Wolf-Rayet stars are extremely hot and massive stars that are losing mass at a rapid rate. They are characterized by strong stellar winds that eject large amounts of material into space. WR124 in the constellation Sagitta is a Wolf-Rayet star surrounded by a nebula of ejected material. Asymptotic giant branch, or AGB, stars are stars that have evolved past the red giant phase. They experience periods of instability and mass loss, creating beautiful planetary nebulae. Mira in the constellation Cetus is an example of an AGB star. Section 9. Stellar remnants, stellar graveyards. When stars reach the end of their lives, they leave behind remnants that mark their final fate. These remnants, shaped by the star's initial mass and the processes of its death, offer valuable insights into the life cycle of stars and the fundamental laws of physics. White dwarfs, as previously mentioned, are the remnants of low-mass stars like our Sun. These Earth-sized embers, composed mostly of carbon and oxygen, gradually cool and fade over billions of years. Neutron stars, formed from the collapse of more massive stars, are incredibly dense objects. Their extreme gravity and magnetic fields make them fascinating laboratories for studying extreme physics. Pulsars, rapidly rotating neutron stars, emit beams of radiation that sweep across the cosmos like cosmic lighthouses. Black holes represent the ultimate end for the most massive stars. These regions of space-time, where gravity reigns supreme, are still shrouded in mystery. Scientists are actively studying black holes to understand their properties and their role in the evolution of the universe. Section 10. The cosmic tapestry of stars. The universe is a vast and wondrous tapestry woven with threads of starlight. Each type of star, from the smallest red dwarf to the most massive blue supergiant, plays a crucial role in this cosmic drama. Main sequence stars, the workhorses of the cosmos, illuminate the universe and provide the energy for life to flourish. Giants and supergiants, with their immense size and luminosity, serve as beacons across interstellar distances. Dwarfs, both white and brown, represent the endpoints of stellar evolution, while exotic objects like neutron stars and black holes push the boundaries of our understanding of physics. Variable stars, with their rhythmic changes in brightness, provide astronomers with valuable tools for measuring the cosmos. PreMain sequence stars offer glimpses into the birth of stars and planetary systems, while PostMain sequence stars paint the universe with the remnants of their stellar demise. As we continue to explore the universe, we uncover new and more fascinating details about the lives and deaths of stars. Each discovery adds a new thread to the rich tapestry of the cosmos, enriching our understanding of the universe we call home.